let's get back to it then. So I want to do one more interesting example of a DFA. By now you have had a lot of practice with the DFAs on the homework, I hope. I hope that you feel like you are beginning to get the hang of it. It is something that takes a bit of getting used to, trying to express yourself in the language of DFAs. In my opinion, all the examples that we did so far and the examples on the homework are kind of cutesy, but not very like computer-like, in my opinion. I wanted to do an example now of a DFA which actually does an interesting computation, and a computation that actually is something that I am not really able to do very well in my head, for example. But you can make a DFA that is fairly simple, that actually does the computation very well. So this fun example here, this is a DFA for binary numbers. So can we just talk briefly about binary numbers, first of all? Numbers in binary. You know, we human beings tend to count with numbers using base 10, but for many reasons, lots of things inside computers are easier to express when you use binary. That is base 2, which means the only digits you use are 0 and 1. Like in base 10, we use digits 0 through 9. There is no digit for 10. When you get to 10, you go up to the next digit. And in base 2, there's no digit for 2. There's only 0 and 1. And when you get to 2, you go up to the next digit. So this is just, I think probably most of you know about this, but just to make sure we're all on the same page here. If I count in decimal, that is base 10. That's what the deck in decimal means. That puts the deck in decimal. It goes like this, 6, 7, 8, 9, and then there's no symbol for 10, so you roll over to the next digit. In binary, those same numbers look very different. Well, 0 and 1 look the same, but maybe I'm going to write these closer together so that you can more easily line them up. 0 and 1 look the same, but 2 looks like 10. You go up to the next digit in binary when you get to 2. And then you count up from 10. Of course, after 10 comes 11. After 11, I can't go 12 because I can't use the 2. I got to go up to the next digit. And in fact, you go all the way up to something that looks like 100. Surely you know the hilarious math joke. There's 10 kinds of mathematicians. The ones who understand binary and the ones who don't. You got to think about that one for a little. Because 10 is 2 in binary. You get it? That's why I said 10, but I meant 2 because I was thinking about binary. That's why it's funny. So I'm trying to count along here. It's not really a good idea to try and convert 5 into binary. It's actually easier to just count straight in this way. After 100 comes 101. After 101 comes 110 because I want to count up in this digit, but I have to carry over to the next digit, count up there. Then is 111. Then is 1000. That's 8. 8 is a very nice sort of round number in binary because it's a power of 2. Next comes 1001, then 1010. If I wanted to continue, it would be like this. This is not so difficult if you get used to it. And then finally, that is 16. 16 is the next sort of, oops, I went off the bottom. 16 is the next kind of nice round number in binary because it's the next power of 2. All right, those are the numbers in binary. And what I would like to demonstrate is you can actually make DFAs that do interesting things using binary. Of course, you can do this in other bases, but it's actually easier in binary to make a DFA that does what I'm about to say. Our DFA, it's going to be a DFA which reads a binary number. As usual, it's going to read it like a string that is from left to right, which is a little weird. I mean, ordinarily, at least when I think of reading a number, I sort of read a number from right to left. rather than left to right like an ordinary word. The reason we write, anyone know why we write? The way that we write numbers is kind of backwards. It's kind of right to left rather than left to right. Anybody historically know why this is true? I think you will all know once I say it. It's because we use the Arabic number system, and the Arabic numerals come from Arabic, which is a right to left written language. And so a lot of the way that we write numbers is inherited from the Arabs, who it made more sense for them to write it than the other way around. Anyway, a DFA which reads a binary number left to right, just because that's how our DFAs always work, left to right, and accepts if it's divisible by 3. All right. This, in my opinion, is a very cute trick that a DFA can do that actually for a human being, like for me, it's not very easy for me to do this. Can you look at, like on this, of these binary numbers here, maybe I'll circle the ones which are divisible by 3. And here, right? Those are the numbers which are divisible by 3. Did anybody see the pattern there? Or you might, another way to think about this is, how about I just give you a big binary number here? Anybody know if that one is divisible by 3 or not? The answer is, no, I do not know. This is something that people learn, like kids learn sort of tricks for telling if something is divisible by 5 or by 2 or something. Or maybe it's not so hard to tell if a base 10 number is divisible by 3, but a binary number like this, at least off the top of my head, I don't know if this is divisible by 3 or not. And if I really had to know, I suppose I would just convert this to base 10 somehow by multiplying out powers of 2. It would take me, if I were doing this by hand, it would take me a couple minutes probably to figure out if this number is divisible by 3 or not. But I'm here to tell you, there is a DFA which can do this, and actually very quickly. And in fact, you could use the DFA to do this yourself. If you had the DFA diagram, you could just sort of follow the arrows, and you'd be able to tell if this is divisible by 3 or not, based on whether the DFA accepts or not. But this is where we're going with this. The point of this example is just to demonstrate that DFAs are kind of cute and simple, but they are sort of powerful enough to do actually interesting computations, things that you couldn't necessarily do in your head, things that are not obvious what the answers are. The DFA can actually tell you if that is divisible by 3 or not. All right, let's see if we can do this. It's not at all obvious how you would make such a DFA, but it turns out we can, oh, you see that? That's what happens when I don't use my sleeve. We can do it with 3 states, in fact. So it's actually a fairly simple looking DFA when you look at it. It's not at all obvious how to do this, but you can do it using only 3 states. And the 3 states has to do with, yesterday we talked about a machine that decides evens versus odds, and you probably did similar things on the homework. We can do this with 3 states because when it comes to being divisible by 3, as you all know, when you divide a number by 3, either it is divisible, or it's not divisible because there's a remainder of 1, or it's not divisible because there's a remainder of 2. Those are the 3 options in fancier terminology. The 3 states correspond to the value of this number when you go mod 3. Is it 0 mod 3, which means it's divisible, or is it 1 mod 3, or is it 2 mod 3? So we can do it with 3 states, and they represent sort of x equals 0 mod 3, x equal 1 mod 3, or x equal 2 mod 3. And I hope everybody knows what I mean by that. I mean, when you divide by 3, the remainder, it's either a multiple of 3, or it's like 1 more than a multiple of 3, or it's 2 more than a multiple of 3. All right? Those are going to be my 3 states. So when I draw my diagram, maybe I'll start drawing the diagram here. This is going to be 0, mod 3, that's one state. I have a state which is 1 mod 3, and I have a state which is 2 mod 3. All right. The big question is, where are you going to put the arrows? All right. Maybe before we answer that's the hard part. What about anybody want to say what should the starting state be? This is before we start reading the number at all. What do you think?
0 mod 3?
Yeah, the starting state is you're looking at the empty string, a number of no digits at all. I would interpret that as the number 0. The number 0 is divisible by 3, so I want to start in that state. All right? And we could also decide what should the accepting states be. I said I want the DFA to accept if it's divisible by 3. So which one is he accepting?
0.
That's the 0 mod 3 state. That means it is divisible by 3. All right. The big question here is where to put the arrows. So this is what we need to talk about in more detail. But this is the basic setup. Fairly easy to get started. All right. The big question is, where do the arrows go? So what we need to wonder about is, how does the value change when we read a new digit? All right, that's what we need to think about in terms of figuring out where the arrows go, because the arrows are meant to describe where do you go when you see a new digit, or when you see a new letter, where does it go to? And I thought maybe by way of example, we could just think about, let's say in a very specific example, what if the value that I've read so far is 101? This corresponds to the decimal number 5, if you look back at a little chart that I made. That's the number 5. What happens if the next digit I read is a 0? I want to think about, and also what happens if the next digit I read is a 1? Now, if the next digit I read is a 0, that means the number now is 1010. Remember, I'm reading digits from left to right. So if I had seen what I saw before was 101, and then the next digit is 0, that means actually the number I'm talking about now is this. And this number in decimal is 10. This is 10. Whereas if I had added a 1 onto the end, that would look like this, like that, right? And this is the number in decimal, that's the number 11. I hope you can see my 2 colors. Yeah. All right. This is something that seems, at least when I look at it, seems very confusing on the surface, but actually, if you think of it in the proper way, you can tell fairly easily what's going on here. Can anyone describe, maybe in terms of the value of this number, it used to be 5, then I added a 0 onto the end, it became 10. Does that make sense to anybody? Can you say, like in general, what's going to happen if I have some number and then I add a 0 on the end? What does that do to the value of the number? Yeah. It will double it. Yeah, I think I agree that if you add a 0 onto the end of a binary number, the effect is to double that number. Can you say why? Does anybody have a feeling about why that might be? It is a true fact. Putting 0 on the end doubles the number. It's true. This is actually similar to in base 10, if you put a 0 on the end, the effect of that is it multiplies the number by 10. And the reason that's true is because basically if you have a base 10 number, all the digits represent powers of 10. And by adding an extra 0 onto the end, you're shifting all the digits to the left by 1, which means you're increasing all the exponents by 1, which is the same thing as saying you multiplied everything by an extra 10, because you're increasing the exponents on 10s by 1. The same is true in binary. If you add a 0 onto the end of a binary number, what that means is you shift all the powers of 2 up by 1. And that is the same as multiplying everything by 2. All right? So putting a 0 on the end doubles the number. So when you put a 0 on the end, it's like x becomes 2x, right? This is the effect of putting a 0 onto the end of a binary number. It changes an x to a 2x. What about this one, putting a 1 on the end? This does... Anyone got an idea for this? Yeah.
Is it double it and add 1?
Yeah, 2x plus 1, I would say. Double it and then add 1, he said. Yeah, I mean, whatever, this is a little more complicated, but putting a 0 on the end, like these two numbers here, whatever this one is, it's just 1 more than that. So if putting a 0 on doubles it, putting a 1 on doubles it and then increases it by 1, because it's just 1 more than if you had added a 0 onto it. All right? Putting a 0 on the end doubles the number. Putting a 1 on the end changes the number like this. X becomes 2x plus 1. All right? So now, where do the arrows go? Knowing this, it just comes down to, if I know that my number is divisible by 3, and then I put a 0 on it, is that number still going to be, where does it become now? So let's try and think about this. So I'm going to do the arrows from the 0 mod 3 case. From this state, right? If I go x, if x equals 0 mod 3, and then I see a 0, it becomes 2x, which is mod 3. Is this now still 0, or is it now 1 mod 3, or is it now 2 mod 3? Anyone have a feeling about this? Another way of saying this is, if you start with something which is divisible by 3, and then you turn that into, and you double it, is it now still divisible by 3, or is it 1 extra or 2 extra? What do you think?
0 mod 3.
I think it is still divisible by 3. If you have a number that's divisible by 3 and then you double it, the result will still be divisible by 3. I don't know if that seems obvious. If this doesn't seem obvious to you, I don't think it's exactly obvious. But the way to work this out would be you start by observing that x is 3 times something. And what that means is that 2x is 2 times 3k, which is the same as 3 times 2k. And so that means 2x is 0 mod 3, right? I rearranged this stuff a little bit, but anyway, you can see that 2x is still a multiple of 3. That's what all of this algebra is meant to explain. If I begin with a multiple of 3, and then I multiply it by 2, the result is still a multiple of 3. 3 times something, and so 2x is 0 mod 3. And that means the arrow in the diagram up here, labeled with a 0, goes back around there. Like that, right? If it's 0 mod 3 and you see a 0, it's still gonna be 0 mod 3. Okay, what about the other arrows? We just need to do like little arguments like this each time, okay? So let's say, again, if x is 3k and if you read a 0, it becomes 2x. If you read a 1, remember it becomes 2x plus 1. And then what is that in terms of mod 3? Well, this would be 2 times 3k plus 1. And again, you can just rearrange this business a little bit, and it looks like that. And now you can see this is 3 times something plus an extra 1. And so this number here is 1 mod 3, because I got 3 times something plus an extra 1. And so on my diagram, the arrow labeled with a 1 goes over to the 1 mod 3 state, like so. All right. There are 4 more arrows. Remember, every state needs 2 arrows coming out, a 0 arrow and a 1. So I need the 0 and the 1 from here and the 0 and the 1 from here. But, I mean, these, we just will figure them out in the same old way. So let's talk about 1 mod 3 now. If x equals 1 mod 3, so this means x equals something like 3k plus 1. It's a multiple of 3 plus an extra 1. And what happens when I read a new 0? That turns it into this. 2 times 3k plus 1, right? Because reading is 0 doubles the number. So it becomes 2 times 3k plus 1. And then I want to somehow work this out and figure out what is the remainder of this when you pull a 3 out to the front of it. The way to do that would be distribute the 2. You get 2 times 3k plus 2. But then this is 3 times 2k plus 2. So this is 3 times something plus 2, which means this thing is 2 mod 3, right? It's a multiple of 3 plus an extra 2. So that means the 0 arrow from the middle state goes over to the 2. Sorry to constantly be scrolling up and down. All right? And similarly, that was reading is 0, which is multiplication by 2. What if I read 1 from this state? Then it would become 2, 3k, 3k plus 1, like that. And I hope you are doing fine with your parentheses. This is 2 times 3k, come on now, 2 times 3k plus 2 plus 1. That is an extra plus 3 on the end there. So this is 2 times 3k plus 3, and I can factor 3 out of all of that. So this is 0 mod 3, because it really is just a multiple of 3, right? 3 times that other stuff. So this means from the state in the middle, the arrow with a 1 goes back to the 0. That's what that means. Like this. With a 1, sorry. Like that, right? And then finally, I need 2 arrows from the state on the right, and we just do very similar little algebra things. So for the state on the right, that's when x equals 2 mod 3. That means that x looks like 3 times something plus 2. And if I multiply that by 2, it becomes 2 times 3 times something plus 2. Which, if you recombine everything, this says 3 times 2k plus 4. And when I go mod 3 on that, the 4 sort of turns into a 1 mod 3. This equals 1 mod 3. And so that means from the rightmost state, if you see a 0, it should go back to the state in the middle, back to the 1 state. So here, like that. And then finally, a 1. If I'm in the rightmost state and I read a 1, that means this number becomes 2 times 3k plus 2 plus 1, like that, which if you expand and whatever, you get 3 times 2k plus 5. This is 2 mod 3. And so the arrow, the rightmost arrow, goes back to itself with a 1. Like that. And that's my final answer. So this is a DFA which can decide if a binary number is divisible by 3 or not. I think that's rather cute that this works out into something that is so easy to easy to look at. It took a few minutes to derive all the arrows, but it works quite nicely. Can we just test it out? How about this number here? 1100 is divisible by 3. So that means on my chart here, 1100, I start here, I go 1, 1, 0, 0. I hope you were watching the dot. 1, 1, 0, 0. It is accepted. Whereas, say, the next number, 1, 1, 0, 1, should be rejected. That's 1, 1, 0, 1. Ends up here, so it's rejected. All right? It seems to work all right. And what about this silly big number here? I asked you before, does anyone know if this is divisible by 3 or not? I can figure that out without even knowing what that number is in decimal. You just sort of follow the arrows. I go 1, 1, 0, 1, 0, 1, 1, 0, 1, 0, 1, 1, 1, 0. It's over here. So this, whatever that is 2 mod 3, which means it is not divisible by 3. Pretty cute, I think. So DFAs, they are very, very simple, but actually they are still capable of doing what is, in my opinion, at least a somewhat interesting computational task. All right? Great. Any thoughts or questions about that? Excellent. You could imagine I can imagine other interesting tasks which could be solved by DFAs, although they would be much, much bigger DFAs. You could, for instance, make a DFA to play a perfect game of tic-tac-toe or something, where you would start with, start with this. That's the starting state. And then you would make arrows for every possible move and include them all in the diagram. This would be a massive diagram, but you could make accepting states for when your guy wins. And then the DFA would be able to take a sequence of moves and tell you whether or not that was the best possible sequence of moves to win the game or something like that. This, I suppose, could be a little bit useful, although the DFA would be really big. Like, you wouldn't ever really want to print this thing out and follow the arrows while playing a game of tic-tac-toe. If you want to get really crazy, you could imagine a DFA for something like a Rubik's Cube, which would have many, many, many different states for all the possible configurations of the cube. But it could still, by following paths through the DFA, you could see sequences of moves which get you to solve the cube. They are useful in theory. Again, you would never actually want to do that in real life, though. All right. Excellent. I would like to talk a little bit more formally now. So that was maybe the last sort of interesting example of a DFA that we're going to talk about in class. Here is another example just to get us started talking about some kind of formal considerations. There's some homework problems like this. I draw a DFA and then you tell me something about it. All right, this is a DFA. I think I put enough arrows in there. I would like to ask about this DFA. Which strings will be accepted and which are rejected? Which strings are accepted? I think you have some homework problems like this to work on for tonight. Anybody got an idea how you could say this, like in ordinary language or as a set perhaps? Maybe I'll just say, like, okay, which strings are accepted? I can just start writing them down. The empty string is accepted. A is accepted. AA is accepted because those would just start here and do like this. If you just do A's, that will be accepted, right? Or you could do something like AAB, that's also accepted because you do AA and then B, you end up here, which is an accepted state. This is not an exhaustive list. I'm just sort of spitting out some strings which are actually accepted. Rejected. Can you give me an example of something which is rejected? Yeah? BA is rejected, yeah. Because that will go B and then A, and that's rejected. Or something like BAA, right? That would be BAA. You end up in the rejected state over here. Can anybody say, like in words in general, how would you describe all the strings which are accepted here? What do you think?
Any string that does not have an A after a B.
Yeah, any string that does not have an A after a B. That's one way that you could say this. This accepts any string without A after B. I think that makes sense. When you look at the diagram here, I think you can tell by looking at it what causes you to get rejected. The only way you can get rejected is if you somehow do a B first and then an A later, right? And if that happens, you're going to, the B doesn't even have to be first. You could do other stuff, but what makes you get to this rejecting state is if you do a B and an A after that B. Can anybody say more like, can you say this in a more affirmative way rather than This is somehow a negative type statement, any string except whatever. Maybe I have another way of saying that in a more, like this describes what the strings do not look like. Can you tell me, like, what do they look like? Maybe I'll write some more that are accepted. A, B, B, A, B, 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 B. Yeah, you have another.
They're kind of alphabetical, I guess.
Alphabetical? Yeah, yeah. I think I know what you mean. You have another way of saying that? Okay, it starts with A. Yes. I would say it starts with perhaps more than one A. It has.
It's got one more A than a B.
This is true of all the examples I drew, but it's that's coincidental. I mean, like this doesn't have, yeah, but it has. Sorry, that is also accepted, right? I would describe this as just like some number of A's and then some number of B's, but nothing else, right? Some A's and then some B's. This is equivalent to what he said before, any string without an A after a B. But I would say, I don't know, somehow this is just another way to think about this. Any string without an A after a B, this is equivalently, or any string with, can I say, a block of A's followed by a block of B's. Where by block, I mean the blocks might be of size 0, so they could be like empty blocks, because it's possible there are no A's, it's possible there are no B's, but a block of A's followed by a block of B's. This, I prefer this just because this is easier to write as a set. So as in using sort of mathematical set theory notation, that is fairly easy to write. I would write it like this. A to the n followed by b to the m, where n and m are natural numbers. Remember, this natural numbers just means any positive whole numbers or possibly including 0. 0 doesn't count as positive, but it counts as a natural number in this class at least. All right, so this means some bunch of A's first followed by some bunch of B's. This is the same as any string without an A after a B, but that is harder to write in this format. So we're usually going to write things in this format in this class at least. All right. Great. That set right there has a name. This set is referred to as, this is called the language of the DFA. Remember on the first day we talked about alphabets and languages. In this example, the alphabet is A and B. Those are the letters. And a language is just any set of strings. And so this here is a set of strings. And so we can refer to it as a language. And this is the language of the DFA. This is also sometimes called the language accepted by the DFA. These are synonyms. All right. And if the DFA, oftentimes the DFA, we give it like a name, like a variable name or something. So if the DFA is M, I'm usually going to use M for machine, then L of M, this is the language accepted by M. All right, the language accepted by the machine. All right, that's called the language accepted by the DFA. And one of the major questions that I was trying to ask, or just encourage us to think about before, was what kinds of things can you do with the DFA? The DFA can decide, whether something is even or odd. It can apparently can decide if a binary number is divisible by 3. But it can't decide everything. An equivalent way of asking this question, what are the capabilities of a DFA? We could also ask, and this is really the same question, what are the kinds of languages which can be the language of a DFA? It's the same question when I ask you, what is a DFA capable of computing? It's the same thing as asking, what kinds of languages can be the language of a DFA? And there's a word for that. So this I'm going to write as a fancy definition, although it's not really a fancy definition. A language, L, is called regular if there exists a DFA M with L equals the language of M. All right, so certain languages are regular and some are not regular. Regular means it is the language of some DFA. All right, that's what this, I hope you remember this little guy here. Regular means there exists some DFA so that that language is the language of the DFA. So regular means it is the language of some DFA. All right, that's what a regular language is. And so the question of what kinds of things can a DFA do is totally equivalent to the question, which languages are regular, right? And that's the big question that I want to answer about DFAs. Which languages are regular? What kinds of languages are regular? For example, this, a to the n, b to the m, n and m being natural numbers. This is regular. That's because this is the language of that DFA that I just drew a few minutes ago, right? And so that means that is a regular language. Something like a to the 2n. This is also regular. What it means when I say it is regular, it means there is a DFA which has that as its language that it accepts. And what is is there really a DFA which accepts this language? This would be all A's where the exponent is even. And that is a DFA that we saw last time, right? It's this. That's the DFA. That's a DFA whose language is this here, a to the 2n. And so that means this is a regular language. When I say it is regular, it means there is a DFA which gives you that language, all right? Basically everything in this class, you can phrase it in terms of questions about machines, but you could also phrase it equivalently in terms of questions about languages. And our textbook is written mostly from the point of view of languages, which is why the name of the textbook is Formal Languages. Or is it just Formal Language? Anyway, it's a book about machines, but it's also a book about different types of languages. They are equivalent ways of talking about the same thing. All right. Okay, these are examples of regular languages. An example of a language which is not regular. Which languages are regular? Those are. Which are not regular? For some reason, this is not called irregular. I don't know why, but nobody says that word for it. They're just not regular. Which are not regular? Well, this is actually much harder to say. Much harder to find examples. It's because what it takes to show something is regular is you have to say what the DFA is that makes that language, all right? What does it take to show that something is not regular? Well, then you would have to somehow demonstrate that no possible DFA can create this language. And that is a much harder thing to just reason out logically. You have to somehow write some kind of proof, usually a proof by contradiction, that no possible DFA could ever generate this language, which is much more complicated than simply showing me a DFA which does generate this. So it's much harder to find examples, but one that I mentioned last time was something like x in, maybe I'll write this in a somewhat fancy way. You may have seen that star thing there. Maybe you've seen this on the homework. This is something that I mentioned once in class, but I quickly moved on to something else, and I haven't made much of a deal out of it since then. But this star, I hope you all remember, the star means all possible strings using what's inside of that set. So what this x in a star, that means x is any string using a's. So it could be the empty string, it could be just a or AAA, and so on. Anyway, this means all strings of just a's where the length is a prime number. It turns out that is not a regular language. You can't do this with a DFA. Another way of saying that is there is no DFA which reads a string and tells you if the length was prime or not. Another thing that's not a regular language, I'll just give you another example. Something like a to the n, b to the n. This one looks very similar, but it's not exactly the same as the one you can see at the top there. The difference up here is this is n and m, whereas down here it's n and n. Can anybody, what is actually the difference between those two sets? I mean, okay, it's the m versus the n, but what difference does that make in terms of this, what kinds of strings are in each of those? They are not the same set, yeah.
In the one with the n's, there's the same amount of a's and b's.
Yeah, this one requires that there's the same number of a's and b's, whereas this one, they don't have to be the same number, all right? But otherwise, they're the same set. So this has some amount of a's followed by some amount of b's. This is the same, but there has to be the same number. It turns out that this also is not regular. There's no DFA which can do this language. That may be a bit of a surprise because this is not so complicated, but it turns out no DFA can do this. So these are, can I just say, hard to prove. We are eventually going to come back to this and talk about non-regular languages and how to demonstrate at least that the second one is not a regular language. The first one is a little weird, and I don't really want to get into it. Prime numbers are too weird for me. In general, I'm not a number theorist kind of guy. All right, those are hard to prove, I'll just say. We'll come back to it. All right, what I would like to talk about for the remainder of our time today is the true definition of a DFA. So our DFAs are diagrams, right? But mathematicians like us don't like using diagrams for definitions. This is probably something you're familiar with. We don't typically define things by pictures. Like when your friends ask you, at lunch before class, when you talk about the theory of computation with your friends, they say, what exactly is a DFA again? And you're like, oh, well, it's this thing with the circles and arrows and the accepting states. Your friend might say, it's really just like a thing with circles and arrows. That's not a very good mathematical definition of a thing with the circles and the arrows and such. Because we don't like diagrams for definitions. For example, if I showed you, here's a very simple DFA. This is like one of the simplest possible DFAs. That's a DFA, right? The alphabet is just A's and it accepts everything. Isn't that nice? Very accepting gentleman. Versus, how about this? Check out this DFA. Huh? I made the arrow extra curly. Your friend at lunch might ask you, is that the same DFA? And you say, yes, he was just being silly with the curly arrow. Okay, but that's not the same diagram, right? Those are two different diagrams with the curly arrow versus this one over here. If your friend really pressed you, you would be forced to admit, okay, yes, the DFA, like the diagram is not what the DFA really is. The diagram represents the DFA. It is a picture of the DFA, but that's not what it truly is. This arrow being curly or whatever doesn't matter, because that's not what's important about how curly the arrow is. What's important is what it really is. And then your friend will say, okay, then what is it really? What is it really is if it's not the diagram? And this is what I want to talk about for the next little bit. It is not really the diagram. The diagram is a picture of the DFA. What is the true nature of the DFA? This is like a stoner question. Like, what really is it, man? If it's not the diagram, what is it really deep down inside? This is what I want to talk about. So really, it should be definable without the diagram. The diagram is a picture of it, but that's not what it truly is. So what the DFA really is I would say, a collection of abstract ideas. But if you want to do real mathematics with it, you should express everything in the language of set theory using sets and functions. So this is what our book refers to as the formal definition of a DFA. The formal definition of a DFA. This is a definition that does not use the diagram as part of the definition. The diagram is a way of indicating or representing the DFA, but that's not what it truly is. If you've taken real analysis, for example, you know that formal definitions are often way more complicated than you want them to be, like the definition of a continuous function or something is far more complicated than you expect. The true definition of a DFA is actually nowhere near that bad. So I don't know if this sounds like a bad idea to you. It's not really very complicated. It's kind of complicated looking, but it's very easy to understand. We should think about, maybe I'll just draw my old example again. This is the A to the N, B to the M example. Just so that we have something to look at while we are trying to think about this. We need to somehow, from the diagram, distill down all of the important ingredients. So a DFA, in some kind of theoretical level, has, actually, it can be boiled down to 5 important sort of types of information that are carried by the diagram. I'll say ingredients. All right. And the very first one is kind of actually sometimes slightly ambiguous when you look at the diagram. But the first one I'm going to say is the alphabet. Right? In this case, the alphabet is A and B. All right? In our example here, it's A and B. This is a set. What else do you what other information do you see on the diagram? Yeah.
Starting state.
Yes, you see. Can I say actually before that? You see what are the states first of all. The diagram tells you what the states are. There are 3 in this example, but there are the states. Right? There are 3 of them in this example. Also indicated on the diagram, what he said is which one is the starting state. That is indicated on the diagram by that first arrow there. 2 more things you can see on the diagram that are important. What else?
Accepting objective states.
Yes. Which are the accepting states? So formally speaking, I'm just going to say what the accepting states are, and then the rejecting states are all the other ones. And what else? One more important thing on the diagram. Somebody else. Maybe someone I haven't heard from. One more, yeah?
The state transition.
Yeah, the arrows on the diagram, which are called, like he said, the transitions. All right? Now, these are the 5 ingredients that we need to represent as part of the definition. And I said I want to represent all of these things in the language of mathematical set theory involving sets and functions. And actually, pretty much all of these can be fairly easily represented by either sets or functions. This one, the alphabet, is a set, right? It's A comma B. The states, that's also a set. In this example, there are 3 of them, and if you want, you could give them names, and then you could actually write down specifically what, if I call the sets like X, Y, Z or something. I mean, the states are X, Y, Z, those are the sets. Those are the states, it's a set. What about the starting state? Actually, this is not a set, it's an element of this one, right? I had a set of states to tell me what is the starting state. That's one of the elements of that set. So that's easy to describe. The accepting states, that's a set also. It's in fact a subset of this one, right? And then the transitions, those are the arrows. Now you could think of them as a set of arrows, but it's a little more convenient to think of the transitions as represented by a function because they are arrows that sort of go from here to here. They have like an input and an output, or a starting and an ending. So the transitions we are going to represent by a function. All right? All of this should be fairly easy to express using sets and functions. All right? So I'm going to tell you the true definition now of a DFA. It has 5 ingredients. So here's the true definition. A DFA, deterministic finite automaton, which I will call M, is a 5-tuple. M equals. We're just going to take these 5 things and bundle them together into a tuple. And we're going to call them this: Q, sigma, delta, Q0, and F. Where, and I'm going to tell you what each of the 5 parts means. Next time you're talking to your friend at lunch about what a DFA really is, you can tell them this, and they will understand nothing of what you're talking about because it's so abstract. Where? All right, Q is a finite set. This is the set of states. So these are written in a particular order, and the order in which they're written is, first you write the states. Next, sigma, that's the alphabet. So sigma is, and what is the alphabet? It's just some other finite set. This is the alphabet. Next is delta, and this is the function which carries the information of the transitions. So delta, I'm going to write as a function. And I hope you remember from like your discrete math class, when you write a function, you write its domain and its codomain with this colon. The way I'm going to write this, well, I'll write it first and then try to explain what this means. It's from Q cross sigma to Q. And this is called the transition function. That's the most complicated part, and we're going to come back to that, explain what all that means. But let me just, it's easy to explain the other 2, so let's just say what the others are. Q0 is an element of S, and this is the starting state. And then F is a subset of S, and this is, sorry, I don't mean S, I mean Q. There is no S, it's Q. This is the set of accepting states. All right. This is the true nature of a DFA. What it is, one way to say this to your friend is, what is a DFA? It's a thing which has states and a transition function. and it has a starting state, and it has a set of accepting states. That's what it is. And your friend will say, what do you mean a thing? And you say, it's an abstract thing, and I don't have to tell you anything else about it. It's a bunch of sets and a function all bundled together. All right? If you want to, you can draw a diagram of it, and that helps you to understand what it really is. All right? We should discuss the transition function. That's the most complicated ingredient of this whole thing. But if I were to use this example again, my old example that I've drawn 2 times already, let's just try and express this example using the formal description. So the states here, I'm going to call them S1. You have to give them names if you want to discuss them in terms of the set theory. I'll call them S1, S2, and S3. All right. So here, let's just say what each of these things are. The Q is the set of states. That is, you would write it with the curly brackets, S1, S2, S3, right? Every set is written with the curlies. The sigma is the alphabet, which is A and B. That is to say, it is the set A comma B. That's the alphabet. The delta is a function which is more complicated. I will leave that to the end. The Q0 is the starting state. On the diagram, you can see that is S1. The F is the set of accepting states, which in this case is S1, comma S2. All right. So this is the formal description of the DFA so far. We also need to discuss, and this is maybe the most important part, or the most interesting part, is the transition function, this delta. The transition function, delta, and I will remind you, its domain is Q cross sigma, and its codomain is Q. What that all means, I hope you have some memory of this from your discrete math class. It means what you plug into delta is something from Q cross sigma. And what the cross means, this is the product of 2 sets, which is the set of all pairs, where the first thing is from Q and the second thing is from sigma. So what that means is the way you write down what delta looks like is you plug in a pair, something that looks like S1, comma A, where the first part of the pair is a state, and the second part of the pair is a letter from the alphabet. That's what this Q cross sigma means. The first part of the pair is one of the Q's, and the second part of the pair is one of the sigmas. That is a letter. And then the answer is one of the Q's. It is a state, all right? So the answer is one of the states. And your interpretation of this is this little function value is meant to describe where the arrow goes. And when you read this, what this means is when I'm in this state and I read this letter, where does the arrow go? If I'm in state S1 and I read the letter A, where does that arrow point to? And the answer is it points back to S1. So this equals S1. All right? This is one value of the transition function. And your interpretation of this, what that means is when in S1, if I read A, then I go to S1. This is how you interpret that little value of the transition function. All right. Now that's not the entire function. Sorry, I'm off the bottom. That's not the whole function. That's just one of the values. But that is the first value. How do I describe the whole function? You just write down all the values. So a full description of the function in this example. I'm going to wreck my shirt like this. The way to describe this function is just to write down all of its values. So this is somewhat tedious, but I'm going to write down all possible values of this function. S3 of A and S3 of B. We just have to say what each of these are. Individually, these values correspond to the 6 different arrows, right? There are 6 values here. Me telling you what these 6 values are is equivalent to telling you where all the arrows go, right? And so, looking at the picture, can you still see the picture on your paper? I hope so. Delta of S1 and A is S1. That means if I'm in state S1 and I see the A, it goes back to S1. What about the S1 and B? Somebody shout it out. Yeah, this is S2 because on the diagram, if you're in state S1 and you see a B, it goes over to S2. So this is S2. S2 and A, if I'm in state S2 and I see A, it goes over to S3. So this is S3. S2 and B is S2. That's because S2 has a looped edge on it with the B. And then S3 on the diagram, both of the arrows loop back to S3. So this answer is S3 both times. All right? And that is the full delta. All right? So, can I just summarize here? This has been a bit rambling, but all of this is an effort to give a formal description of this DFA right here. Maybe I'll copy it down just so we can still see it. This would be a typical homework or test question. This is, it might take you a little while to write down your answer, but this is very easy. It's just a matter of knowing where everything goes. It would say something like, they would give you a picture and then say, give the formal description of the DFA. And then your answer would be something like M equals, okay, it's a 5 tuple. The first thing is the set of states. You have to get them in the correct order, technically. So this would be S1, S2, S3. The next thing is the alphabet, which is A, B. The next thing is the transition function, which is a big thing that you have to write all the possible values. You can't squeeze them into the tuple, so I usually will do it this way. The next, and then down here I'm going to say where delta, and then I'll describe the values of delta down there. Anyway, the next thing is the starting state, which is S1. And finally, the set of accepting states, which is S1, S2. And then where delta of S1A equals S1, delta of S1B equals S2, delta of S2A equals S3, delta of S2B equals S2, delta of S3A equals S3, delta of S3B equals S3. The end. This is the formal description of the DFA. So this right here, that is what the DFA really is beneath the diagram. Yes?
So you want to put the delta on the bottom rather than like putting it in?
Yeah, to me, that makes more sense than trying to write all of that right in there with the comma. Yeah. I mean, this is how I would always write it this way. If you want to write it slightly differently, I suppose that's a free country, but that's how I'm going to do it. All right. I hope you agree. This is very easy to do. It's just you have to know where to put each of the ingredients. I suppose you have to remember what the ordering is. It's the states, then the alphabet, then the function, then the starting state, then the set of accepting states. And it's also very easy to go the other way around. If I presented to you all of this stuff, you can use that stuff to draw the diagram, right? It has this many states. And then by looking at the values of the delta, that shows you where the arrows go. So these are really interoperable. It's just that this one is preferable from a formal point of view because it is being expressed in the language of sets and functions rather than just a picture that you have to look at. All right, this is the true definition of a DFA. All right, great. We have a few more minutes. And I would like to discuss, so from this point of view, it's my big question, which I think we can answer in the remaining 7 minutes. What is the definition of L of M. Remember, that's the language accepted by the DFA. The set of all strings which are accepted by the DFA. Can we somehow, I want to write this as a set. L of M equals the set of, where in here, I'm going to use some kind of notations from here with the delta and the whatever, right? I'm going to somehow indicate it's the set of all strings which are accepted here. Now, if you're looking at a diagram, what does it mean to be accepted? It means if you follow the arrows with your finger, you end up in the double circle thing. I want to say all of that in a formalized way without talking about my finger or the arrows, right? Just talking about these formal ingredients. Towards that end, there is a sort of convenient thing that we often talk about. We'll often use what's called the extended transition function. The extended transition function. And this is written as delta star. And delta star is like delta, but its domain is this instead of what it was before. Q cross sigma star. I hope you remember, the star means all strings. So what this looks like is when you use delta star, you put a state here, but in the second coordinate, instead of just a single letter, you put a whole string in the second coordinate. So I could put something like A, B, A in the second coordinate, all right? It works the same as the ordinary delta, but it is, it takes a whole string as its second coordinate rather than just a letter. And then what does this mean? It has the same meaning though. It means if I start in state S1, and then I follow arrows for A, followed by B, followed by A, then what is the state that I end up in? Can anyone still see the diagram? If I start in S1 and I do A, B, A, where do I end up? S3, I believe. Yeah, if you start in S1, you do A, B, A, you end up in S3. So this, in this particular example, is S3. Right? If I start in state S1 and follow that string, I end up in state S3. All right? Can I give you 3 simple properties of the delta star? Actually, 2 simple ones and 1 somewhat strange one. Maybe we'll have to end on the strange one. These are like bullet points here. And I want to say this is a simple property. What do you think this should mean? If I start in state Q and I do the empty string, where do I end up? I would say Q again, right? Wherever you are, if you do the empty string, follow the arrows for the empty string. That means you don't go anywhere and you end up in the same state again, all right? So if I'm in a particular state and do the empty string, then I end up in the same place. How about if x is a string which happens to have length 1, remember the absolute value signs mean that it has length 1. That means that x is just a single letter. Then delta star of q and x. Well, then it equals just delta of q and x. Because if it's just a single letter, then doing a string which consists of a single letter is the same as doing the ordinary transition function, which works with single letters one at a time. All right. Here's the most interesting one, which we have 2 minutes to discuss. It's this. What is delta star of q and x followed by y? The idea is if I start in some state and I do some string x and then some other string y, that should somehow be the same as like doing x and then doing y. I want to write something, don't write this because this is wrong, but something like delta star of qx followed by delta star of qy, right? Like you do x first and then you separately do y. But this, what I wrote here doesn't make any sense because I just like wrote 2 things next to each other, but that's not sensible. Like the answer is supposed to be a particular state. You're not supposed to, you can't write 2 deltas next to each other. This is not what I mean. Anybody feel me when I say this? What do I actually mean to say over here? It's actually a little weird to write it down correctly, what I mean by this. I mean, you start at Q, you do X, and then from there you continue and do Y. Any ideas? We've got 1 minute on the clock. You got an attempt, an idea?
I guess you could write that, and then you could also do after that whatever the answer to delta star QX is.
Yeah.
You could change the Q into whatever your answer is, and then put Y.
Mm-hmm. I like the sound of this. So he says you do that, and then plug in. I think this is what you meant, right? To this, blah, 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 comma Y, right? Is that what you meant?
Yeah.
Yeah. Anyone think? Actually, you could write this better than what I just did. How would you write that in a more fancier way? Yeah.
You could do delta star, and then in that blob you could do delta star QX.
Yeah. I like this. Delta star QX.
Y.
Oops. Comma Y. Yeah. That's what it looks like. This is the third simple property. It looks very complicated, but it's a very simple idea, I think. It's just, it ends up looking complicated when you want to write it correctly. All right. And unfortunately, I think we'll have to leave it at that. So, watch your email. I will tell you exactly what video content I would like you to watch. Please like and subscribe. And I hope you have a good week and a half. I'll see you next Friday. We'll do the quiz. And let me know if you have remaining questions about the homework. I'm going to hang around. I mean, I have another class in this very room at 2, but we can talk for a few minutes right now if anybody would like. Or else you can send me an email and I'll try and help out.